So this is a model of
If anybody wants to come up, they can come up here.
this is a model of a tank house that we built to demonstrate straight current and arc flash. And it's a working model. We actually have current flow through the cells. We are plating copper, so it's as close to realistic as we can be.
Could you speak up just a little bit?
Yeah. There are 3 safety features that were built into this model so that we don't hurt anybody, you know, as we play with it. Number 1 is we've limited the voltage. So our maximum voltage that we can put on the rectifier is 40 volts. And that's below the 50 volt maximum that you're allowed under the National Electrical Code. So we are inherently safe when it comes to voltage. Even if you, the other safety feature is the amperage. If we had used a battery, a 12-volt car battery or something, if we demonstrated an arc flash, we could actually cause an arc flash. So this rectifier is limited to 5 amps of output, and it cuts itself off. And so we can't really demonstrate arc flash. We don't get much of a spark, but it's safe. That's why we did it. The third item is the electrolyte. Normal electrolyte has sulfuric acid in it, 160 gram per liter. You know, that's about 15% sulfuric acid. In a classroom environment, we didn't want to use acid, so we have made a synthetic electrolyte that simulates the conductivity of electrolyte, but it is not electrolyte. So I can touch this electrolyte and not get burnt, okay? So it's safe. So we start by showing the rectifier is this box right here. We are connected between the rectifier to this wire right here, and it connects to the bus bar right here. The power comes into the bus bar, enters the first cell at the apron, goes through the anodes and cathodes, through the intercell bus, jumps, keeps on coming down, goes back into an apron, across the crossover bus, back into an apron, and then through the intercell buses and the anodes and cathodes, back into the bus bar and back into the rectifier. So that is a true EW circuit. Now, just because we didn't want to use lead in the classroom, we decided to go with copper anodes, copper cathodes, which is more of electro refining circuit. So it's truly electro refining, not electro winning, but the current and the voltages are very similar. Okay, so we also have a crane here, so it's a movable crane, and the trolley can go back and forth, and we're going to use that feature to measure paths to safe, shock hazard. We have a conductive cable here. It's actually made out of copper, and on the end of the cable we have an insulator. So I made a little insulator right there. So even though this is a metal hook here, I even went so far as to, I was very impressed because it actually has a safety catch on it. Just to make sure we're MSHA compliant, but the paint sort of made it so it doesn't work anymore. But so even if I touch here on this metal component, and the insulator will prevent the current from going through. If I touch above the insulator, then the current will flow, and we'll see that. The current will go up through here. I've taken the paint off here so that the power will go through into the frame of the crane, and then it'll go down through here into the rails. These are made out of brass to make them conductive, but in real life they would be made out of steel. But in real life we would have 480 volt motors on this crane, and there is actually no connection between the DC circuit and the 480 volt circuit, but inside the wire of the 480 volts is a ground wire, and that ground wire is what allows the power to be going through into the building ground, because the 480 volt circuit is grounded to the building ground. So here we have the crane rails. Here, these represent the columns in the building. So the columns are painted like they are in a real building. And to simulate a corroded paint, I've actually removed some of the paint right here. And I will be using that spot to demonstrate current flow. In the real life, you would have a column that's corroded, the paint is peeling, it's the same thing. You have to be able to touch the metal in order to get the current to flow. If you have a perfectly good column with good epoxy paint on it, that in itself is a safeguard, but you don't really want to totally rely on that because paint fails. Okay. So we start off by, in a real life circuit, if you want to turn on the rectifier, just say you have a typical voltage. What's a typical voltage supplying a rectifier, anybody?
200.
No, the AC side? 13.8? Yeah, that's kilovolts, 13,800 kilovolts. There's a set of big switches there that close and allows that AC current to go into the rectifier. Inside the rectifier, it was mentioned, it gets converted, the voltage gets dropped down to the proper voltage, and it gets converted from AC to DC so that we can plane copper. So this switch represents the AC switch, so that turns on the AC. I still do not have, if you look at the voltage on this scale right here, I should be 0, 0, right? So that demonstrates that the rectifier is, there is no flow through the bus bar because the rectifier, there's a switch in there that hasn't been closed yet. In this case, it's probably an electronic switch, it's not a big knife switch, but in order to close the knives on the DC side of the circuit, you have to push 2 buttons. Of course, it doesn't work. There we go. What voltage do we have going through the circuit right now?
32.
Yeah, and the amperage?
1.6.
Yeah, okay, so that's good, that's good. So this here is a voltmeter. And it basically will give us the same signal that's there, but the advantage of this one is that I can, the voltmeter on the rectifier only tells me what the voltage is right there on the input. So what I can do with this one is measure voltages in different places. So just to convince ourselves that this thing is working, I gotta get my polarity right. I don't know if I got it right. Is that, this voltage, is that going the right way?
Yes.
Okay, so how many volts do I have?
30-something.
Yeah, it's overscale, but it's about 32, should be 32 volts, okay? So that just shows you that, sure enough, that the voltmeter on the rectifier is the same as what we're measuring here. Okay? So I have 16 cells here, so there's a voltage drop across every cell, so who knows what the voltage is across one cell?
Two.
Two, thank you. And we will demonstrate that. Get my polarity right, correct me if I'm wrong, but about 2 volts, okay? Now, if I go down an extra cell, what should it be?
4.
Okay, 4.
Yep.
Next one is
6. 8. 12.
I'm gonna jump up to the last one.
16.
Yep. And I'll go halfway down this cell house
24.
and all the way down for the whole circuit, back to 32 volts. So that demonstrates that it's just like a real tank house, 2 volts per cell. And the farther down you go, the higher the voltage. So the hazard one of the hazards in a tank house is arc flash and shorting out between these two rows of cells. And you'll, in the talk, we had this distance of 42 inches from an energized surface to a grounded surface. So these walkways on the side, here and along the ends, are typically 42 inches or more, and that is to provide you enough room to walk down these walkways without touching yourself between the energized surface and ground. Now, on the center walkway, the potential is even higher, because you can actually go directly from energized surface to energized surface. And there is, when you go through the ground and through leaks, and there's resistance, that's kind of helping you. But when you're in the center walkway, there's nothing there. It's only you against the voltage. And so, what's good to understand is that various places in the tank house, the risk of shock hazard and arc flash varies depending on where you are. So if you were standing right here and you touched, well, first of all, if you go and somehow touch the bus bar, you get 32 volts. Right?
Yeah, it's a
Very
cable.
good.
So,
Yes.
thank you. Red is positive, in case you didn't know. And in a real tank house, this would be like, if it's times 10, it would be 300, over 300 volts, right? And so if you direct connect 300 volts to a person, and your resistance is 1,000 ohms, that's 320 milliamps, you're basically dead, except for your PPE, which we don't want to rely on. But so that's really bad to touch the two bus bars, and that's why we guard those bus bars. There's a fence around the rectifier. As you go into the building, these bus bars have guards around them. There should be no way of touching those bus bars. Sometimes they put them at lower voltage tank houses, they put them up high in the air, so you can't physically reach up and touch them. So if you go from here, if you touch here to here, you get like 30 volts or something, right?
Yeah, 28.
And then, but if you come down here and touch this one to this one, you get 2 volts,
Yeah.
right? So that's the demonstration that the risk varies depending on where you are in the tank house. But because the risk is so high at this end of the tank house, we make this walkway, we like to make these walkways super wide. So we take, if we say if 42 inches is safe here, then we like to make this like at least like 84. We double that because of the increased risk on that central walkway. So you walk into any tank house in the world, you'll see the outside walkways are like a typical walkway, and the center walkway is a double wide walkway. It's there for a reason. It's electrical safety. And we'll get into that a little bit more, where we talk about putting conductive equipment in that center walkway is always increasing your risk of arc flash and shock hazard, because you're bridging that safeguard. Okay, so one other thing I wanted to show you, we tested this this morning, but it didn't work, but see if it works this time. And so if I go from here, got my clarity right? So if I go from here to here, where do we get?
28.
Something, yeah.
Mhm.
Okay, so what I have here is a electrolyte pipe, and it's made out of plastic. This is made out of PVC, and here we have a piece of metal. And there's electrolyte in there, but you can see that there's no metal connecting this cell to this metal fitting here. So what do you think, when we tested it this morning, we had air trapped in there and we got 0 volts, but now that we remove the air, what do you think what voltage do you think I would get if I touched that piece of pipe there?
2.
2 volts.
Or 28 like you did the other.
Yeah, so
Yeah.
32 volts, because we are, this bus bar is connected to that anode, and that anode is taking the power into that cell. And that cell, that electrolyte is conductive, and so it just brings that power straight out to the fitting. So think of that when you're down in the basement, away from all your energized surfaces, those pipes are energized.
Okay, so you basically went from here to here then, kind of,
Yeah,
right?
yeah, it's very, there's hardly any there is a difference, because copper is more conductive than electrolyte. So, you know, if I go from here to here, I get 32 volts, and then if I go here to here, it should be, it's like 31 volts, because there's a 1 volt drop across that electrolyte. Another way of looking at this is, you can actually demonstrate it. I was playing with it without the electrodes in. I think the electrodes kind of mess up the experiment, but I actually had it with no electrodes in. I was sticking the voltage into the probes into the electrolyte, and I was actually getting,
Okay, you do get some.
you know, it's only if I touch the, but you actually can measure the voltage in the electrolyte with no electrodes. It's kind of neat.
You're making it bounce a little bit?
Yeah.
Who's touching?
Yeah, but I actually touched the electrodes. I think it's because the electrodes are in, it's not working very well. Okay, so what I wanted to show you was, one of the concepts here is that the cell line is a floating circuit. We have insulators on the bus bar to make sure power doesn't go down into the basement. But I forgot to mention insulators under here, under these cells here. And also the cells are made out of Lexan, and it's non-conductive, just like polymer concrete is. And so we have two levels of protection. With the plastic cells, stop the electricity from flowing into the floor, and also these insulators stop the flow of electricity. So, if I measure voltage from an energized surface to here, I get 32 volts like I showed before. Now, if I measure voltage from here to here, what do I get? Zero. And that's because we have a true floating DC circuit. There is no connection in this circuit right now between the cells and the floor steel. So how many people have worked in a tank house that's perfect and has no leaks? Yeah, me neither. Actually, I've started up a few tank houses, but probably about an hour after you start to have leaks, or even sooner. But there is like a 5 or 10 minute time when you can actually go into a tank house and not have stray currents. But once you start to have the leaks, you've got stray currents, and you have to assume that they're there, because it's a big safety concern.
And that would also isolate your block in your book if you had no leaks.
Yeah, that's a good example of what I'll show you that, you know, so here, just I've got my polarity, so if I go from there to there, I got nothing. And if I stand on the cell that's energized, like we know that's energized, right? This way. We know that's energized.
Mhm.
And if I bring, and this is still energized, if I bring that up there, and it'll be zero. No. Because the ground system is totally separated from the DC circuit, one path to ground will not allow electricity to flow, and you're safe. So now we get to the interesting point. This is
What
the-
material do they typically make the hook insulators from?
You know, it varies. Teflon is one, because it's acid resistant. You don't want those insulators to absorb electrolyte.
Mhm.
And I've seen them in Teflon, polypropylene, and ceramic, I think, are the three common ones. But they're maybe Bakelite, like some of the older cranes might use Bakelite of some sort, but it doesn't really matter. The, insulators at this level of voltage is basically anything will be an insulator. You know, any plastic will be an insulator, as long as it doesn't have carbon in it. Carbon messes up things. You know, it'll make a plastic non-insulator into a conductor. Okay, so this gets to be some interesting things. So these two things right here represent the fingers on a human being, okay? So I'm gonna go through and touch different things in the cell house. And the reason why this simulates a human being is because the electricity will go through the ammeter, so this gives us an indication of amp flow. So 100 milliamps is the same milliamps that's on that chart up there. When you get up to 100 milliamps, you have a risk of killing, of stopping your heart, okay? Just keep in mind that yes, we have an amperage that if it got through my heart, if I would stop it. But because the rectifier is limited in voltage, then it's not enough to go through your skin. If I had cuts on my fingers and I touched this, then yes, my heart would probably stop, or could stop. But as long as the low voltage is what's saving me and making this safe to demonstrate, okay? So one thing I do is that demonstrate this, and so I'm gonna go do a direct short, and boom, nothing happens. And the reason is because I got my PPE on, and these are gloves, so boom, boom. Those are my gloves, okay? That is what normally saves you in a tank house. And the boots, okay? Your boots are the same thing. But as I found out when I was working one day about right here in a tank house, I picked up the feed line in my hand. It was a rubber hose, and I was standing on fiberglass grating that was covered with electrolyte, and I didn't have my gloves on. But it was okay because I had my rubber boots on, and I bent down, picked up the pipe, and I got knocked to the floor with a shock. And what it was my boot had a crack in it. It was failed. So I was down to one level of protection. The fiberglass walkway had electrolyte, so it was conductive. My hand was conductive because I picked up the pipe with my bare hand. And my boot was conductive because it had a crack in it. So we don't want to rely on PPE to save us. It's there as an additional, I call it belt and suspenders. If the belt's good, then belt and suspenders are even better. So it's an added layer of protection. So this is gonna be as if we don't have PPE on. So if I start by doing a direct short across here, I'm gonna do it real quick because backwards, same thing. Red is positive. I have to remember that. So I can't do this very long. It'll probably wreck the meters, but it'll basically go off scale. Do that go too?
Mhm.
Okay, so that demonstrates that if you touch across a bus bar, that is the most hazardous thing you can do in a tank house. If you come down here and do the same thing here, it's gonna go off scale as well. If you come down to the end one, 50 milliamps. You'll, on the chart there, that was involuntary muscle contractions. Okay? So, one end of the cell house, you're dead. The other end, and if you're down here, you actually get 0 because there is no voltage potential there. But if you go from anode to cathode, it's 2 volts, and you will get. I'll just do it this way. There it is there. You get, what's that?
Like 2.
20,
So
30 milliamps. Okay? So that's a demonstration that direct shorting or becoming part of a circuit across energized surfaces that isn't going through the building ground, you know, no leaks or anything like that, it's just direct connection is like the most hazardous thing in a tank house. And the other thing that's hazardous in, you know, for direct connections, so this represents a J-hook, okay, look, I lost my real one, I don't know where it is, but if you drop that across there, then you get arc flash, just like in the real world, okay? And if you go farther down, I'm looking for a longer one because that one wasn't long enough. If I go down here, then it's not as bad, okay? So there you're getting arc flash. Here, there's 0 voltage potential, there's nothing. So that's a demonstration that within the cell house, or the tank house, your risk of arc flash varies depending on where you are. The closer you are to the rectifier, the higher the risk. So in some plants, they have to bridge across the center walkway. It's always better to do it away from the rectifier, but the best is not to do it at all, okay? Like some tank houses, you're just not allowed to do it. But if you have to do it, it's always better to do it at the end of the tank house, opposite the rectifier.
Well, where does current play into this? Cause our rectifier at Sierra Rita is only 48 volts. But it's 29,000 amps.
Yeah, so, how many volts?
48?
48? So, it's at 48 volts, the National Electrical Code says that anything below 50 volts, you don't have to worry about. But there are documented cases where people have been killed at 48 volts.
Well, that's why I'm saying, where does current play into it? Cause like I said, our rectifier's putting out 29,000 amps
Right,
at
so,
48 volts.
so that's available to go through your body, but because of the resistance of your body, you take, let's say, 50 volts, and let's say you're fairly dry, so you've got 1,000 ohms of resistance, and 1,000 into 50, then you'd have 50 milliamps is the maximum. So even though you have potential, if it's cold cranking amps, it's 300, and I think it's times 5, it's about 1,500 amps available in a car battery, and it'll just have melted screwdrivers. Just, and imagine what it'll do at 29,000. Not only you're going from 12 volts up to 40 volts, but you're also going from like 1,500 amps up to 29,000 amps. So horrendous arc flash hazard.
And the amperage is what you receive the shock from. Difference of potential, the more amps flow, the more serious your shock is.
Right, well, that's why I brought it up. 48 volts is typically nothing, but 29,000 amps at 48 volts.
Right, and milliamps are thousands of an amp. So when we're talking 50,
Electrical code says you have to do it. You have to do it.
So if the electrolyte is ponded up,
Right here?
well, where those electrical grounds come off the beam, right? They're bonded to the beam, the steel beam, right?
Yeah.
And then they
So-
run into the concrete, right?
Yeah.
And if electrolyte's ponded up to where that little
Yeah.
short piece of copper wire is, it's a good
Yeah,
connection
but-
to the ground,
and-
right?
And then if there was a leak in the pipe that was running over to that pond, then there's your path. That's your way to get into the ground.
and concrete is a relatively good conductor all by itself.
Or you could become that path if you kneel down in it, so you're bypassing your rubber boot. So you kneel down in that, you kneel down in it, and then you go to touch it. Now you have your rubber glove on, but let's say I reach across that leak and I make contact with my forearm. I've now made that connection.
So you guys' tank house, you guys got panels, right? So in your panels, if you had bare wires hanging out of the panels, would it concern you? Well, when you have electric like laying on the ground, that's like bare wires.
Or sulfate buildup?
Or something.
And that's all, we're gonna go through all that still, it's all coming up still. But exactly, you guys having that understanding is that's what this class is for.
There's one other concept that I want you to understand, and that is that if you have a leak out here and it goes through the floor and it comes back in the circuit, that can lead to a hazardous situation. But in the center walkway, there's usually pipes as well. Now, some plants have and some don't, but most of them do. And this, when that pipe is connected to, like, approaches the rectifier end of the tank house, okay? What happens to the potential, if you touch that, if that pipe has a leak and this pipe has a leak, and those pipes quite often are like, I've got photos, and I think they'll show, but they're usually, you know, can only be, some of them are only 3 feet apart, and you can touch it with your elbows.
So that minimum, instead of 42 inches, you always
Right.
want, now all of a sudden you have less than that.
We like to
in the
keep
most
42
hazardous.
inches down there between those pipes, but, you know,
Right,
not
that's how
always,
it
they're
goes.
not always there. Some, what was it, Baghdad, it was wonderful, it had like 10 feet between them, perfect. No way could you, like, well, you could, but it's hard, okay? So, what I wanna show is the difference, when you're working down in the basement, you think you're away from the bus bar and I don't have to worry about that anymore, but if you go from here to here, now this represents the pipe, the pipe out here is the same as in here, basically, okay? But- So, pull. Wow, 300 milliamps. Okay, now what happens if I go down here?
None.
Nothing. You see? Now, if I go from here to here,
You're not in the solution.
thank you. I'll go positive. So there. So from ground, because if I go to ground, from the leak or the pipe to the ground, I have to go through all these other leaks to get back in the circuit. But if I go from leak to leak, then here it's more. And so here's leak to leak, or I mean, leak to leak in the center walkway, in the basement. That is your most hazardous place.
Essentially, you're becoming another leak. You're becoming a parallel resistor in there. Just, these would be carrying just as many milliamps as he's reading over there when you touch
And
it.
what's not discussed very much in Safford, where the accident happened.
Yeah, it was right here up
Was
front.
at the rectifier end of the tank house. If it had been at the other end of the tank house, it would have been,
Could have been different.
could have been different. But,
The understanding is wearing proper PPE and not having that knowledge to know kneeling in something and touching another part of your body creates that path. And not having that knowledge is why we have this class, because that's what caused that.
The knowledge will help
fatality.
you with your safe work practices. Your PPE is like your last line of defense, a hierarchy of controls. When you're down on your PPE and your behavior, you got a lot of risk. If you can start putting other things, good work practices helps your behavior to be safer.
not,
So think of the things you guys been doing in the tank house and how close you've been to being killed. That you guys have been getting away. So if you're in Safford and they understand the severity of what happens. And you guys need to get there, where it's not acceptable to be shot.
so, there's one last thing I want to show, and that is conductive tools. We've already shown you what happens if you have a conductive tool, the arc flash, okay? So what happens if you're working in the basement with a conductive tool and you accidentally touch the bus bar? And that's the situation here. So you're down in the basement, you're holding this conductive tool, you accidentally touch the bus bar, boom, 150 amps, you're dead. That's why that bus bar is guarded. But typically, they use guarding with holes in it. And you can still poke things through it, you know. And you got to make sure nothing conductive goes in through those holes. In one place, one plant I inspected, I always look for conductive things around bus bars in the basement. So I'm down there looking, you know, I'm down here looking up here, looking to see if there's anything that's of concern. And I found this one piece of metal within inches of the bus bar. And I looked at it and I thought, is that a pipe, a piece of conduit? Didn't know what it was. Looked at it and it turns out it was somebody thought it was a really good idea because a J-hook was a tripping hazard. They stored it by dropping it through the holes in the walkway, and they were within inches of the live bus bar, and they were standing like you know, in some cases, this bus bar comes across and goes out to the rectifiers out here. So if that, in that case, he could have gone out and touched that bus bar, standing on the cell, and he would have had full rectifier voltage through that. Conductive tools in a tank house. You know, when I do high voltage tank houses, they're all fiberglass. You don't use conductive tools. But, you know, if you're gonna use them, you have to insulate them, or if they're truly conductive, they're a risk hazard and you have to evaluate them. You know, you understand the risk. What is it? Administrative controls, training, procedures, all that sort of stuff. You gotta think about those tools. Does anybody have any questions? I can demonstrate anything else if you've got it. Like, I think I covered everything, but has anybody had a shock in a tank house? So, where was your shock?
Underneath in the flash house, underneath the cells, changing boards.
Boards, what's boards?
We have boards underneath the cells that.
Oh,
our
wood,
liners
the
sit on,
wooden
the
boards.
wooden boards,
Yeah, okay. So, the wood is wood, okay, and it was saturated with electrolyte, and wood normally is an insulator, but we don't like using wood in modern tank houses because it absorbs electrolyte and it very quickly becomes conductive. And that board was probably up in the bottom of the cell, and it got energized and it became part of the path of the ground. So I can't demonstrate that here because I got plastic cells, so, but it's kind of obvious that one.
Well, should we
Anybody-
consider, didn't we try, pieces of wood that were coated with, Teflon?
We did, but they don't hold up, they sag and then they fall out.
Really, they're worse than
Yeah,
just
they
the wood by
end up-
itself,
They end
huh?
up blowing in and they just.
You know what the wood is, right? You know what the wood's for, huh? It's to hold up the parallel liner.
Yes, oh, yeah.
You know,
Yeah,
you got
yeah.
the parallel liner.
I mean, modern tank houses, they use polymer concrete. So anybody else had a shock in the field, in the tank house? Where was?
It's on the cell line.
So where were you? Can you point to where you were?
I don't know, like about in the middle. So
In the center walkway.
Got the crane up no, we were pulling samples. So I was on the cell.
Oh, on the cell,
On
yeah.
the cell, we were pulling samples.
Yeah.
And
And-
went single pull.
Yep, single
Set
pole.
my hand on the crane block to swing it out.
Crane block.
Mhm.
So crane block to an energized electrode. So we covered that one. We got that one.
I had rubber boots on. I didn't have the right gloves on. The insulator and the hook was bad.
Did you touch your arm? or
Oh
something?
no, I couldn't push it far enough with one hand, so I put my other hand on it and it.
Made better contact, more better
Oh yeah.
It probably went through your feet.
No, it went straight through it.
But going to the same electrically potential on both hands.
When I pushed, when it broke contact with the cathode, that's when it shocked me.
Yeah, but it probably would.
You
go
felt it in your
through-
hands, but
through-
you felt it
You
through
felt it
your
in your
feet.
hands, but it probably went through your feet.
Pick up samples by pushing the block?
Well, no, our old single pole got damaged, and we're using I don't know, not the proper one for the job until we got the new one in. Yeah. So
So that one-
you'd
So you're
basically
holding the
you'd
triangle?
basically have to get down on your hands and knees to move
Hands
that.
and knees where you're touching your.
No.
No?
If you didn't do it that way, that's how you would have to get the single pole out.
So that would be an interesting one to look into more detail, how, the electrical engineer, anybody? Who's our electrical engineer? How could you possibly get electrocuted if both ends are on the same potential? That, to me, I'm not quite sure how that would work, but I mean, it happened, so,
Yeah.
you know, it happened, but just because I don't understand it doesn't mean it's not a hazard.
So in order for him to get shocked, he touched the crane block. It must have came through his boot. If that's how
I
it's
would have
supposed to.
expected that.
Was he holding up whatever he's gonna lift that sample with? Because that would give you two.
Yeah, because I'm thinking that he touched, or I don't know how it happened, but maybe he touched this and then went on the other side of the insulator to the hook, which was
No,
already connected to the cell. Or
This ground plate, it is totally separated from the DC circuit, and you can't have flow if you only have one connection. So what we've done here is to demonstrate a leak. So we couldn't drill a hole in our cell and have electrolyte all over the floor. So what I did, we made up these little leaks, and we call these leaks, and they're just a basic copper wire, and there's a resistor buried in here. that has the ohms sort of equivalent to an electrolyte leak. And it's connected to the ground floor, to the concrete, through this alligator clip. So it's grounded, and if I put that in there, that's the same thing as a leak coming out through the pipe. It's allowing electricity to come from that cell through here into the floor. So now, if I go back to my fitting, what have I got?
20 milliamps.
20
30
milliamps.
But still zero, no volts.
I just don't have, I don't have.
Ah, okay.
Okay, I could hook those up. Yeah.
Okay.
Okay, so that demonstrates the hazard of a leak. Now, here I have resistance because there's electrolyte there, but what happens if, say, you touch an energized surface and the building steel? It's 50 milliamps, okay? Because the steel has lower resistance than the electrolyte in that pipe. So touching, what that tells you is touching a pipe isn't as bad as touching grounded steel, okay? So the risk level has gone up. But in this case, it's not so high as to be a problem because you're only at 50 milliamps, and we know by our chart that probably 99% of the people are going to survive that.
So when I'm doing cell maintenance and got to go down in the trench, and there's electrolyte down there, and I have my rubber boots and all my PP on, and I'm waiting down there waiting for the guy to say, "You ready to start flow?" And I rest my arms on the building or hang like this. You know, I have all my PP on. The only thing that's stopping me from getting shocked is my gloves and my boots.
If you were touching between an energized surface and a building ground, and you had leaks somewhere else in the tank house.
Okay, so yeah, there's electrolyte on the ground because it's going to the drain.
Assume there's a leak.
Yeah. And then this is the floor, and then there's the containment walls, and I'm standing on there. And then there's the steel building, and there's siding and panels everywhere, and all this is connected, right?
Yeah.
And then the only thing that's stopping me from getting a little shocked is my PPE and my gloves, huh?
Well, you'd have to touch an energized pipe.
Okay.
Because then it goes through you to ground.
Okay.
What he's saying is, in the center trench, we drain the cells out.
Yeah.
So there'll be electrolyte draining.
But there's
So you're
pipes.
standing-
There's pipes there.
So you touch the pipe and you're standing in electrolyte. He's saying that the only
Yes.
thing that's stopping you from getting shocked is PP.
Yes.
Okay.
Yes.
And then in Safford, our drains are on the outside,
Yeah.
just like
It
this
doesn't-
example.
doesn't
Yeah,
matter
yeah,
where
yeah.
they are, they're energized. Yeah.
Okay.
The farther away the pipes are from the tank house, so if you go down to the tank farm, you know, if you're like 300 feet away from the tank house and a 300 volt rectifier, then probably you don't have a hazard anymore. But the closer you get, because of this resistance in this pipe, the longer that pipe, the more the resistance, the lower the hazard. And we've demonstrated that by showing that just that much electrolyte reduces the amperage. And that carries on. The longer that pipe is, the lower and lower the amps. Okay, so what I've demonstrated is one leak. How many people have worked in a tank house with only one leak? So if you want to put another leak in there, we'll see what happens. So I'm going to touch the cell and the floor. So what we had before was 50, right? Boom. 190. 2 leaks. You're almost at the point which you can stop a heart. Let's add a third leak. Yeah, 120. Fourth leak.
And where are you simulating the
150.
leak right now?
I'm going from an energized surface on
So something on the cell line.
to a ground, building ground.
Any leak through the cell line to the building?
No, but what kind of person, where would a person be that would simulate that?
Yeah, standing on this walkway,
touching the pipe.
touching the outer anode. Like if
Okay.
this was the outer anode, and you touch that outer anode and grounded building steel, or a grounded safety shower, or a grounded pipe,
Or the drain.
The crane with a bad insulator.
And I'll demonstrate
Or
that
the
in a minute.
Or touch above, or touch the cable above it.
Yeah, the wire rope is
Yeah,
long.
so since we're talking about the crane, then what do you think would be with 4 leaks and standing on that same electrode, what do you think the amperage will be if I touch the hook?
Nothing.
Should be
Nothing.
below the
Both are
insulator.
nothing.
It should be
Yeah,
zero.
zero.
Yeah.
Okay, if I come up and touch the insulator, should be 0. If I come up and touch the grounded cable, what do you think it's gonna be?
140.
If you got a really good person, they wouldn't make that mistake. You need an electrician running this thing, right? Okay, there we go, 150.
150.
And it's no different than touching this one. Okay? That's why we put insulators in crane hooks. And because of that cable, sometimes on higher voltage tank houses, I always put them up here on the trolley as well, so that, you know, I'll demonstrate that by just, if I put that in there and I put that in there. It might be touching still, but plus minus 0.
What do you do for the trolley motor? I mean, do you just down with it?
You put a coupling between the motor and the gearbox. It is an insulating coupling to make, because the motor's grounded, you have to stop the power from going down the shaft. If you ever do let the power go down the shaft, it'll wipe out your bearings in the motor. So it's really important to stop that current.
So do you have to mount the motor then on the isolating blocks then, so that the frame of the motor isn't tied to the trolley also?
Yeah, you mean everything is
Yes.
different, but yeah.
So with the current fleet, we'll insulate on the trolley.
And there's different ways. You can actually do it by putting the drum on insulators, the bearings that hold up the drum. You put those on insulators, and then the coupling between the drum and the gearbox.
So essentially you're isolating the drum, the wire rope.
Anything to isolate this wire.
Right.
Demonstrate how current the PPE.
Yeah, so, and so I'll go back and obviously if I only put one glove on, then basically I'm safe. Because one pair of gloves, and I don't know if we've done that slide, but it's exponentially better. If we're 1,000 ohms as a human, with one glove on, it goes up to, anybody, is it like 10,000 ohms or something? Like a meg ohms even?
Meg ohms.
Yeah, it's a big number.
Even million ohms.
Yep. But a glove with a hole in it, you're back to a human being. Okay?
So you guys should check your PPE every day, right? And your boots, make sure you've got holes in them, cracks, and your gloves are in good condition, because that's protecting you from being shocked. If electricians' gloves have a hole in and they get shocked, what do they do with their gloves? They throw them, they trash them.
How do the electricians check their gloves? Because I mean, even if they have a pinhole in them, you know, that's your path to
You
ground.
test them. You roll them up, you inspect them, you roll them up. Now yours are a little different, but the other part is if you're standing on your feet and you get a shock, it's telling you not only your glove, your boots, there's something wrong there. Now, like if you kneel down or your elbow touches something where then you have an absolute path. And like he talked about 1,000 ohms if you're dry. How often are you dry in there?
Never.
You're
You're
sweating
never
in
dry.
your hands, so you've done some things that will lower your resistance just by being there. Because that 1,000 ohms, that's just, they got to come up with a number to try to calculate a base. But they didn't base it on people in the tank house.
So there's one last thing I want to show, and so what, to summarize, I've shown what happens when you go across the center walkway and across the bus bar. I've shown what happens if the path is up through the crane, and I've shown what is the path through the building columns, okay? There's one last thing I want to show, and that is the pipe. So what happens if there's a conductive flange in the pipe?
Or a valve,
Or a valve, anything?
keys, anything.
What would people expect right here?
150, same as it.
Because there's a little bit of resistance here.
Oh, that's right, this
It
thing.
is, it's gonna be. So there you go. So it's safe, it's helping you. It's 50 milliamps, so you'll get a shock, but you probably won't die. And what saves you, is that electrolyte has resistance and it's safer. And don't,
But it's also conductive.
It is
conductive,
and the
but-
richer it is, the more conductive it
yeah,
is.
there are so many variables. Don't say that Alan said in the meeting that, you know, it's 50 milliamps, therefore it's safe. You can still, as happened in Safford, it can still stop your heart.
So you guys look at it, don't get in a
is a
situation where
model.
it can't grab a hold of you, right? So you guys are doing your work and you go in an area where you know you're gonna have to grab two things and it grabs a hold of you like it grabbed me. Then that 50 milliamps at 8 minutes is not gonna be good.
And there's one other thing I want to show you, and that is that this is a demonstration of a stray current going through the floor. Like what? Make sure everybody understands what's happening here. Is that when I put myself into that circuit, the power is coming through the rectifier. Most of it's going through the cell, but a little bit is being bled off through the electrolyte, through the person, into the floor ground. It's running through the floor, coming up through here, through the leak, and back into the cell. That's the path to ground. Or that's the path.
Because some of our tank houses are different, but some of them have freaking rubber liner in the floor.